Hello again, this is Galen Pickett, Cal State University, Long Beach. I want to talk to you today about a very useful construction to help you figure out how systems are going to behave using the potential energy of interaction. So that's this energy diagram. It's a concept that's introduced in Chapter 6. So if we have two objects, so here's object number 1, M1, and here's object number 2, M2. They got some distance between them, R. The interaction energy is something. So U of R is a function of R is something. So that it's got some, say, minimum, and then it's got maybe some asymptote. So it's got a local maximum here at some particular R. It's got a local minimum. There are several potentials that actually look like this when you study molecular solids. Or molecular systems. So, what does this give us? These two objects, if we consider them as an isolated system, the energy principle will tell us that the change in the energy of the system is equal to the work from the surroundings. Now, if we think of them as an isolated system, the work from the surroundings is 0, so we have the change in the energy of the system, which equals the kinetic energy of the system plus the interaction energy is some constant. Now let's take, say, some planetary example where M1 is so big that it is basically fixed in place and M2 is the thing which is running around. So there's really just one kinetic energy in the system, that is the kinetic energy of object number M2. Now no matter what the energy of the system is, it is some constant, so I'm just going to call that E0, and we pick what this E0 is by saying where does the object start off. That tells us what potential energy it's got and how fast is it's going. That is what tells us what this kinetic energy is. So let's suppose we start with this particular R0, and we start with a kinetic energy which gives a total potential energy. So the K0 is something we pick. Here's the value of U0. So U0, in this case, is a negative number. If I pick my potential energy, so K0 is my initial value of the kinetic energy, the U0, which is some negative, I add to that K0 and I get the value of E0 on this diagram. No matter how this object moves, it cannot change how much energy it's got. So if I plot what is the total energy of the system, I always get this same value E0. So I could follow this particle as it gets to smaller and smaller r's, but eventually it will get to some point r min where the amount of kinetic energy it's got, which is the difference between the blue line and the red line, is smaller and smaller. Right at that point, k is equal to 0, which means its velocity is equal to 0, so it has to stop and turn around and go back the other way. So one very important property of these diagrams, and you'll see them this way in the book, the part that's underneath the potential energy curve is shaded. That is the forbidden region. A particle can never get there because imagine what would happen if we've got a particle with this energy at this position. Well, its potential energy is way up here at U. In order to have a total energy like so, it would have to have its kinetic energy less than 0. But since the kinetic energy is 1/2 mv squared, it always has to be greater than 0. So the kinetic energy has to be above this line. So this initial energy here has got a maximum spot it can be and a minimum. That's a bound orbit. The object is going to go back and forth between some r max and r min for all time. If I pick an energy which is here, very large energy, now the particle can go out to infinity. It's going with a constant kinetic energy, so its velocity is approaching some constant. It's not stopping, but it's approaching some constant value. It's going slowest here. This is an unbounded orbit. Sometimes it's called a scattering orbit. And you can have different possibilities in here. Let me give you a different potential energy. So let's say the potential energy looks like so. Any orbit with an energy, a total energy less than 0, is going to have some spot where it has a minimum, some spot where it has a maximum. So E less than 0 for this particular energy are all bound. If the energy is positive, no matter where you start off, let's suppose you start off at this R with this much kinetic energy, and you're heading inwards. So you'll go to some minimum spot where you have to stop, and then you will go back out, and you'll go out to infinity. This is, again, an unbounded orbit. And if you've got an energy that's exactly zero, so if I start right here with that much kinetic energy, I go in, I turn around, and I go out. This is the borderline. This is the escape velocity. If you start right here, you need exactly that much kinetic energy. So the kinetic energy is equal to negative the initial u. If you've got that set up, then you will come into some minimum, but you also go out to some maximum. That is, you don't fall back to the ground.